So if you have the features like various distributions, okay. So if you have the features of the various distribution, there may be a domination of the few features which have the larger value on the prediction outcome over the smaller values. That's the reason why we try to normalize the data. We have to scale down the data. We are going to normalize the data into the some particular range between 0 to 1. That is called as normalization. We're trying to keep all the data in the range of 0 to 1 while going for the prediction. So that's what I'm doing here, normalization of the data. Sorry. So to normalize the data, in the Python, we have the sklearn pre-processing import min-max scalar. So using this min-max scalar method, so create an object with the min-max scalar and pass your load data to that object. Then your data will be normalized between the 0 and 1. You can see actually your data is in the range of thousands, 3,377 and 8,841. But after normalization, all the values are coming between the 0 and 1. So this is the piece of code can be used for the normalization. Any type of data, you can use this one for the normalizing the data. So normalizing the data between the 0 to 1, this is used. So normalizing the data is nothing but, I think we discussed already, but once again I will tell. Suppose there is x is some multiple values like x1, x2, x3, so many different distributions we have that assume. How we normalize these data? So first of all, among all the complete data samples, you have to identify the minimum value and you have to identify the maximum value. Now what you have to do? Take first sample x1, subtract x min divided by x max minus x min. So this formula is used to normalize the data. For x2, substitute x2 here. For x3, substitute x3 here. For x4, substitute x4 here. Then all the values will be coming from the original value to the normalized values. So this is the formula which is used for the normalization. We can write the code for that also, but we have a method in the Python that is called min-max scalar, and we are using that min-max scalar method to normalize the data. So after normalization, we have this thing. Then fine. So next what we are doing? That is ready. Now what approach we are going to follow? What approach we are going to follow? Okay. So here the approach what I want to follow here is I want to forecast the load. I want to forecast the load based on the 6 features. The features are I'm going to forecast the load at now it is 15:55. That means 4 p.m. And I want to forecast load based on the last 3 hours load data. That means k minus 1, k minus 2, k minus 3. That means if I want to predict the load at kth hour, then 1 hour before k minus 1, k minus 2 hours before, k minus 3 hours before load I have to use. So I have to use these 3 loads and also last 3 days. That means k minus 24, 24 hours back, k minus 48, 48 hours back, k minus 72, 72 hours back. And last k is the load where you are going to predict. I want to predict the load at kth hour based on k minus 1, k minus 2, k minus 3, last 3 hours, k minus 24, k minus 48, k minus 72, last 3 days. Last 3 hours, last 3 days, I'm going to predict. So you have to rearrange the data like this. So you have to rearrange the data. Previously, it is a completely column matrix. Now, after rearranging the data, so see how we have. So looks like something issue. Here, just a minute, please. Okay, fine. Now see, now I'm getting the load data. Like I'm preparing the load data. Like so, I'm trying to forecast load at kth hour based on the 1 hour before, 2 hours before, 3 hours before, 24 hours before, 48 hours before, and 72 hours before. So now how many columns we are expecting in the data set? Column 1, column 2, column 3, column 4, column 5, column 6, column 7. Out of 7 columns, the first 6 columns are the features, input features, and the last column is your output variable, which you are going to predict. Okay. Now I'm converting into the data frame. So see, I hope you everyone are active right now. So maybe it will be helpful for the participants who are mainly focusing on the implementation. Only for the implementation, not in the mathematics background. So this one will be helpful for you. So now what I'm doing here is I am separating the input features into the output features. So X represents the input feature and Y represents the output feature. So how we extract the input feature? Dataset dot ilog. So dataset is the name of the dataset where we store this complete data, and extract the 0th column to the 6th one. Index 6 means you have to exclude the 6th index in the Python. So 0th index, 0th column, 1 column, 2 column, 3 column, and 4 column, and 5 column. Because 6 features, 6 columns you have to extract and assign to the variable called X. And last 6th column, that is called as the your 0, 1, 2, 0, 1, 2, 3, 4, 5. These are the features. Whereas 6th one is called Y, predicted value Y. This is called the predicted value Y. So you have to extract that X and Y values, input features and output features. Suppose if you are trying to predict the load at a particular hour of the day based on the last 3 hours load data, last 3 days load data, and also last 3 weeks load data, then accordingly you have to change these values. Accordingly, you have to change these two values. So now we are separating the X and Y values. Once you separating the input and output, next step is we are going to split the data. We are going to split the data. So how we split the data? We are using the method called train underscore test underscore split. So for this method, train underscore test and split method, you have to pass your input features. You have to pass your output features. You have to give the how much percent of data you want to keep it for the testing, and remaining will be going for the testing. Sorry, training. So testing data I'm giving the 20%. So that means out of all the samples, 20% of data is dedicated for the testing, and remaining 80% of data is going for the training. So the whole data is split into the training and testing. So that will be assigned to a variables called xtrain, xtest, ytrain, and ytest. So xtrain means so training data input features. Xtest means test data input features. Ytrain means training data output label, output variable values. And ytest means in the testing data output variable values. So like that you have to separate it. So you have to split the data for the training and testing. Once the data splitting is over, now you need to build the ANN model. It is very important. So I hope everyone, uh, can you please respond? Anyone is online now?
Yeah, yes.
Yes. Okay. Thank you, sir. Now, how we design the model, how we design the ANN model, this is a very important code. Till now, what we are doing is the only data processing, data pre-processing. Now we are constructing the ANN model. So these are the simple steps. Suppose if you want to write the code either in the MATLAB or in the Python, based on the knowledge what you have, based on the knowledge of mathematics what we acquired. If you want to write the code from the scratch for this model, it will take very huge time. You require more effort. But in the Keras, so how we can build the ANN model, you can see here. First of all, you have to initialize the model. I am initializing the model as a sequential model. Okay. So for that model, so my intention is C. So I want to build um, an ANN model. I want to build an ANN model. So tell me how many number of input features for this problem? 6 input features. So we have the 6 neurons in the input layer.
Yeah.
6 neurons in the input layer. And I want to add one hidden layer with 64 neurons. And I want to add one other hidden layer with again 60. Why is there 64? You may ask. This randomly I'm choosing. So if the performance is not good, you can change these values. another hidden layer with 64 neurons. I want to take another hidden layer with 64 neurons. No need to take all equal. That's your choice. And finally, there is one, this is called input layer. And these three are called as the hidden layers. And there is an output layer. In the output layer, how many neurons are required?
One.
Only one, because we are trying to forecast the load at a particular hour of the day. At a particular hour of the day, we are going to forecast the load. So only one neuron is sufficient. So this is the architecture. Now, how we build this architecture using Keras, you can see it's very interesting. Very simple also. So, for example, forget about this input layer for some time. Now, for the sequential model, you want to add one hidden layer, one dense layer with 64 neurons. See how I am adding that one. See, in the sequential model, I'm initialized and I'm adding a dense layer, hidden layer, sorry, 32. So you can use 64. If you want, you can use 64 also. Okay. So let us do 64. And so model add one hidden layer, dense model dot add, open the bracket, dense, that means hidden layer, with the number of neurons 64. I want to add the 64 neurons. So you have to take the activation function. We have the activation function in the hidden layer and the output layer. So which activation function you want to use? So just I want to use the activation function tan hyperbolic. So activation equal to tan h, you have to pass. That means I'm adding one hidden layer with 64 neurons with tan hyperbolic activation function. Now for this dense layer, input is coming from this input. So input contains how many neurons? 1, 2, 3, 4, 5, 6. That is mentioned here. So for the first hidden layer, input shape is 6 elements. So six vector, a vector containing of 6 elements are the inputs to this hidden layer. That what mentioned here. Hope you understand this line. So you can change. Now I want to add one more hidden layer on this hidden layer. I want to add one more hidden layer on this hidden layer. Then with neurons 64, implicit 64. And I want to add one more hidden layer. So I want to add one more hidden layer with 64 neurons. So simply keep 64. And I want to use the tan hyperbolic activation function in all the hidden layers. And we have the one output layer and add dense. You have to add one output layer. How many neurons in the output layer? Only one. So it is only one. So I am using the sigmoid activation function here. Here I am using the sigmoid activation function. Why I am using the sigmoid activation function? Because I am normalizing the data. All the load values are coming between the 0 and 1 only. All the load values are between the 0 and 1 only. Actually, original data is in terms of the kilowatts. 3000 kilowatt, 4000 kilowatt, 5000 kilowatt, 8000 kilowatt. But the data is normalized. When I am normalizing the data, all the data will be converting between the 0 and 1. So whatever your ANN is predicting, that value should be compared with your data available in the data set, which is between the 0 and 1 only. That's why I am using the sigmoid activation function. If you use the sigmoid activation function, your prediction is always between the 0 and 1. So your minimum value will be 0, maximum value will be 1. So in between the 0 and 1 only, and your data set also in the 0 and 1 only. You can see your data set after normalization, your last column, that is called your output variable values, all are between the 0 and 1 only. Okay, so that's what mentioned here. Okay, so that's why I'm using the sigmoid activation function here. You can use the linear activation function, no issue. You can use the linear activation function, or you can use the sigmoid activation function in the output layer. But where in the hidden layer, the most suggestible activation functions are, you may go with tan hyperbolic activation function, you may go with ReLU activation function, you may go with sigmoid activation function. But don't try to use those ReLU and tan hyperbolic in the output layer. For the output layer, try to use the sigmoid activation function, mostly for the binary cross entropy loss function, mostly for the binary classification problem, and use the linear activation function or sigmoid activation function for the regression problem. And for the categorical classification problem, you have to use the softmax activation function. Maybe I think Vinod Kumar sir told in the last previous class. So various types of activation functions. I'm suggesting go with sigmoid linear for the regression problem in the output layer, and go with sigmoid in the output layer for the binary classification problems, and go with softmax in the output layer for the categorical classification problem. Okay, whereas in case of the hidden layer, you may go with sigmoid, you may go with tan hyperbolic, you may go with ReLU, you may go with GeLU, you may go with Swish So different activation functions are there. Those unit activation functions, nonlinear activation functions, you can go in the hidden layer. Okay. So this is the what model is developed now. See, so there is the 1, 2, 3 hidden layers, and it is the one input layer and one output layer. Okay. Now simply run this cell. That means now the model is available with you. Now the model is available with you. Now my question is, someone, if anyone is active, my question is, why what the value you are showing is the total number of parameters. I said the total number of model parameters we calculated, right? When I'm demonstrating about the single layer and multi-layer ANN network, I said that number of model parameters. So these are the total number of model parameters. How we calculate the total number of model parameters? Anyone can tell why the model parameters in the input layer and first hidden layer equal to 448? So it is showing 448. That means the total number of model parameters between the input layer and first hidden layer is 448. And this is the model parameter between the first hidden layer and second hidden layer. This is the model parameter between the second hidden layer and third hidden layer. And this is the model parameter between the third hidden layer and output layer. And this 8833 is the summation of all total number of model parameters in the ANN model. Now my question is, how we are getting the 448? Any idea? So this is my model. So this is my model. We have the 6 here and 64 neurons in the hidden layer, 64 neurons in the second hidden layer, 64 neurons in the third hidden layer. So what it is showing is, in between the input layer and output layer, total number of model parameters equal to 448. This is showing. How we are getting the 448? Any idea? I'm asking.
Well, it should be number of neurons into
Yes, sir.
layer
Yes, sir.
one.
Right. So if you want to identify the total number of model parameters between these two, then go with number of neurons in the previous layer, number of neurons in the next layer, plus number of neurons in the next layer. Nothing but this is corresponding to the bias parameter. This multiplication corresponds to the weight parameters. So how many number of neurons in the next layer? NN I will write. NN I will write. So what are the number of neurons in the previous layer for this? If it is a block, so previous layer this one. So it is a 6 multiplied by 64 plus, for every neuron you have the one bias parameter. So 64 neurons, 64 bias parameter. This one. So what the value? 6 4 are 24.
144.
Yeah, 6 4 are 24. 6 6 are 36. I think it is a 384 plus 64. That means 8, 14, and 4. So total number of weights are, model parameters are 448. That's how it represents the total number of 448. And why it is 65 in the last case? So you can calculate this also. Why it is 65 in the last case? We may go over here again. Last case means here. It is showing that. So between these two, for the last hidden layer and output layer, it is showing that 65. Why 65? Again, we can go with the same formula. In between, we have the 65. So previous layer, 64 multiplied by next layer, 1 plus 1. So that is the 65. That's how we are calculated. So here what happened between the second hidden layer and third hidden layer, how many parameters we are getting here? So second hidden layer and third hidden layer, between these two, second hidden layer, third hidden layer, 4160. Wait, the 4160 between these two. So previous 64, next 64 plus next 64. So that's how we are getting. So if you calculate these things, we will get the 4160 only.
Yeah.
So if you calculate these things, so 64 multiplied by 64 plus 64. So we have the 4160 model parameters. So that's what that represent in the Keras. So we have the total number of parameters are, so summation of all these nothing but the total number of parameters. These are the 8833 model parameters are there. Your stochastic gradient descent algorithm or gradient descent algorithm is updating all these 8833 parameters during the training process. When the complexity of the model is increases, your simple computers may not sufficient. So we may go with some DGX stations, workstations. Now we build the model. Now architecture is ready. So architecture is ready, data is ready. What we are going to do now? We have to build the training. We have to enable the training for the model. Model is ready, data is ready. We're trying to enable the model to learn, to train. So before that one, we have to tell the information to the training algorithm, what the parameters we want to use. So that one we have to use model dot compile. You have to pass what objective function you want to consider for updating the model parameters. What objective function you are going to minimize. What objective function you want to consider to update the model parameters. So that is, you have to put last function or objective function that is called mean square error. And what optimizer you are using? I am passing the ADAM optimizer. There are the different optimizers. So till now, what I demonstrated on the whiteboard, that is a stochastic gradient descent optimization. So that is, you can write it as SGD. If you write SGD, that is the stochastic gradient descent algorithm. That backend code is what we were discussing in the earlier. If you call only SGD, so it will call that SGD method, stochastic gradient descent method. And metrics. So which metric? That means once the training is completed, which metrics you want to use to analyze your model. That is called, again, I am using the same mean square error I am using. But in the demonstration, when I'm explaining about the code, I sometimes may consider the mean absolute error. So here I'm considering the mean square error. So that's it. So that means while compile means you have to tell the model. So which object function you want to consider to update the model parameter, which optimizer you want to use to update the model parameter, which metrics you want to use to analyze the performance of the model. Those things are provided. Next, what we are going to do now, train the model. See, just train the model, this piece of code. That's it. You no need to write outer for loop, inner for loop. That stuff is not required. In case for this 8,833 parameter model, if you want to write the code from the scratch, we can. But who are not good in the programming much, it will take much difficulty to write the code from the scratch. That's why most of us, even that means who are not good in the programming, most of the people are choosing Keras deep learning framework to train and to construct, to build the ANN model. So now I'm trying to fit the model. So to train the model, what we require, you have required the training data. So training data is what are the input features in the training data? What is the corresponding output variable in the training data? It is supervised learning. So you have to give the both input data and output data you have to give. So input data is X train, output data is Y train. What is the batch size? So batch size 1 means, so what we discussed till now, that's only batch size 1 only. That means, so you have a data. You have over 10 samples, 1, 2, 3, 4, so on 10 samples. So batch size 1 means pass the first sample, update the model parameter. Next, come to the second sample, update the model parameter. Come to third sample, update the model parameter. Come to the fourth sample, update the model parameter. We have to do it until all samples. That's what we discussed till now. So that is called batch size 1. Suppose if I said batch size equal to 2, then what you have to do? So pass the first sample and second sample. After that, you have to update the model parameters. And later pass the third sample, fourth sample, and later update the model parameters. So 2 samples at a time we are feeding to the model to update the model parameters. That is called batch size 2. That means batch size will decide how many number of samples you are passing to the ANN model at a time while training. Hope you understand. Okay. So that is also one of the hyperparameter to tune to check the performance. You can choose with batch size equal 1, batch size equal 2, like that. Epochs, that means itermax. How many number of iterations you want to run the algorithm? Just I'm choosing the 100 iterations only for demonstration. So if the performance is not good, you can increase. As of now, only demonstration, I kept the epochs, number of iterations, max number of iterations equal to 10. This verbose is nothing but just how we want to display the output here. Verbose 0, verbose 1, verbose 2. How we want to display the output here, only it's showing. I'm keeping the verbose equal to 1 means it will give the outputs like this. Just simulate it one more, train the model, see. So 1 iteration of 10 completed, 2 out of 10 completed, 3 out of 10 is completed, 4 out of 10 is completed. So anyone can tell what is this 862, 1026, 12×4, it is varying up to 1689. Any idea? What is that one? You can see one thing is varying continuously at varying up to 1689. What is that? So that is the sample number. So
Just
sample 1, sample 2, it is updating. So finally, all the samples, 1689 samples are available with the training data. Yes, 1689 samples out of 1689 samples are passed to the model to train. So that's it. End of the training of your model. So that means all the model parameters, 8,833 model parameters are updated. Okay. So now once the ready, then we are going to evaluate the model. So the model is performing well, performing with some loss of mean square error value around 0.0106, almost equal to 0. Now, how the model is performing when there is unseen data is available, whether it is generalized or not. Where it is performing well in the training data. If some new data is coming, whether it is predicting well or not. Now you feed the test data which is not given during the training procedure. During the training of your model, we are giving the only training data, not testing data. Now model is trained. Now test the data. Now give the test data to check whether it is performing well or not. So score. So to test the model, you have to use model.evaluate. To test the model, you have to use model.evaluate. So pass your features, input features in the test data, output variable in the test data. Is verbose only for the display purpose, what you want to display. Just run this one. So in the test data, I have the 14 samples and the loss is almost here also 0.0131. So, okay, let's assume I was happy with this performance, let's assume. So then what we are going to do next step is, so fine, training is over, testing is over. Now I'm happy with the model performance. Now I want to check. I want to give some input data to the model and I want to verify whether it is predicting properly or not. So what I'm doing is I'm taking the one sample from the test data, x test as 0, nothing but first sample in the test data, and giving that information to the model to predict. So if you want to use the trained model for prediction, if you want to use the trained model for the prediction, you have to use model dot predict. So when you are going for the prediction, you have to give one input data. Your model will predict what is the output. So no need to give the output data again because we don't know. I want to predict the data load on the substation at 5 p.m. So now I have to give the load. What is the load available at 4 p.m.? What is the load available at 3 p.m.? What is the load available at the 2 p.m.? And what is the load available at yesterday 5 p.m., day before yesterday 5 p.m., before that one 5 p.m. These 6 values I will give, and my model will predict what will be the expected load in the next 1 hour. That means at 5 o'clock. So here you have to feed only input data. No need to pass the output data because that's what you are going to predict. So now once you are using the model.predict, passing the input data, it will give an output. That output will be stored in some variable called prediction. Okay. Up to now, it's fine. Now my question is, anyone can tell why I am doing all those things? Print, prediction, 0, max load minus min load plus min load. Anyone can tell why I am doing like this? What is the necessity? Sir, you are passing the input data to the model to predict, so it will give the predicted load. Na? Then why you are doing something, you can directly print prediction 0. That's enough. Na? But why you are multiplying with max load minus min load plus min load? Why you are doing this one? So I think someone will have a doubt if someone following. So if anyone, why I am writing that line?
I mean, whether it is correctly getting the output or not. Like,
Yes, sir. Actually, before training the model, we normalize the data. That means all load values are in between 0 and 1, right? So
Yeah.
definitely your prediction also between the 0 and 1. So suppose if we are the machine learning engineers, and yes, model was developed, and if we are feeding the input data, and I'm getting the prediction value 0.8, and I show it to the substation engineer, sir, next 5 o'clock your load will be 0.8. So he will be surprised because his load is between the 3000 to 8000. We are saying that 0.8. So why it is given 0.8? Because the model was trained on the normalized data. So what you have to do? You have to denormalize it. You have to find the actual value, not normalized value. You have to give the actual value to the engineer, not your normalized values. So to get the actual value, I am writing this formula. So why it's coming like this? See, how we got the normalized data? X norm equal to actual value X minus minimum value divided by x max minus x min. So this is the normalization. And this normalized data we are using to train the model. So your output also gives the normalized values only because the model is trained on the normalized data. So if I give the normalized value to my some engineer, someone, they will be surprised. Then you have to give the actual value, not normalized value. So where the actual value is available? This is the actual value. How we got this one? Just pass this one here and move this one here. Then you have the x equal to pass this one here. So x norm into x max minus x min and move this part toward the left hand side plus x min. That's what I'm writing here. That's it. See, prediction value, normalized value multiplied by max value minus minimum value plus minimum value, that will give the actual thing. So you can see here. So see how much load it is. My ANN model is predicting the load of 7,334 kilowatts. Actually, my load is 373 kilowatt. So almost same. Just slightly around 40 change is there. So it is closing almost near to your actual values. Still, if you and your client is not happy with that prediction, then you have to retune the model to improve the accuracy, to improve the performance of the model. Fine. So at the laboratory level, so I collect the data, process the data, train the model, test the model. All the things are completed in the laboratory in my computer. Now what we will do, if we keep that information with you, no use. We are doing a work for the third party. So we have to build some application. So we have to deploy our model into some application, right? So in the previous case, when I'm writing about in the MATLAB, so what mean by the deployment? So deployment is nothing but the just storing the weights and bias parameters and host it into the application, keep it into the application, and your application will use that weights and bias parameters. So here also we are saving the model.save with my model.h5. So this is the my model.h5 that contains all the weights. So whenever, if you want to use the mobile application, you want to develop the mobile application for the load forecasting, just keep this my model.h5 into your mobile application and use it. If you want to build the web application, use this my model.h5 into your web application. In the backend, it will run. The weights will be collected from here. You no need to use the remaining code what you are doing at the laboratory level, not required. Just save your model with .h5 extension and use the .h5 that will be available here now. So I will save this model first. Just model was saved with my model.h5. So we need to refresh this one. See my model.h5. Just download this my model.h5 and keep it wherever you want. So if you want to use the mobile application, keep that one there. And if you want to use the mobile application, keep there. And if you want to build some Raspberry Pi based application, keep there. That's it. So next, okay, sir, once we keep there, then how we will reuse it in the mobile application or web application, whatever it may be, how we will reuse that one. So to reuse that saved model, you can see this code from Keras model, import load model. So model equal to load model, pass the model which you want to load. So already we saved this model, right? My model.h5. Now I want to load the model into some application. So that is case you have to use model equal to load underscore model dot h5 extension. Now you can run this code. So same model what you trained till now, that is available here, 8,833. You forget about what you did till now. So just calling this, we are saving the model and loading the model again whenever you want. Same model will come into picture with weights and architecture. So once we save the model, what we are going to do now? So model was saved. Now what we are going to do? Now we have to, some application we will build. So that application will enable the user to enter the data and see. So from Keras model, import load model, this part is completed. So that what we are doing here. Now I am asking the user to enter the values and all the values assigned to a some vector and that input vector passing to the model.predict and that will give the prediction. But before going to print the prediction value, I am trying to what's called denormalize the value. So it is the normal value into max load minus min load plus minimum load. That is the we're doing. So before that one, I want to tell one thing. I think somewhere here. And see, actually, for the demonstration, I tried with C. If you want to use the tan hyperbolic function, you have to use the tan H. If you want to use the sigmoid, you have to use the sigmoid like this. If you want to use the ReLU activation function, you can use the ReLU like this. And if you want to use the Swiss activation function, you have to use the Swiss activation function like this. So based on which type of activation function you can use, you can write the code like this. It will take care. Yeah. So just I'm getting something 2000, 3000. Some random values I'm giving 4000, 2500, 3500. Sorry, 4500. That's it. See. So it is a predicted load is just it asking user. So if I am a substation engineer, so you are the developer and you developed an application and given to me. Now I am the engineer. I am working operator at the substation level. I am entering the values of the loads, previous loads. Then our application will give the what will be the next 1 hour at 5 o'clock load. What it will be, that will be displayed here. So it will ask what they enter the value 1. That means 1 hour before load, 2 hours before load, 3 hours before load, 1 day before load, 2 days before load, 3 days before load. All the parameters you have to enter and you have to run it. It will give the predicted load there 3707 kilowatts. That's how it is working. And maybe, sir, why you are adding this code? Any idea now why I am adding this code here? While preparing the input vector, I am adding some code here. What is the necessity of this code?
Maybe we are trying to get the actual load here, like.
Right, sir. So when we are training the ANN model, both input and output are normalized and feeding to the your ANN model. So here also, when we are developing the application, actually I'm giving the values like 2000, 3000, 4000, 25 like that. So that input data, you have to pre-process it, you have to normalize it and feed to your already trained model, that .h5 file. And it will do some process in the back end. And it will give the predicted output in the normalized fashion. So then that normalized value will be again denormalized to print the predicted load. So this is how this will be works for the regression problem. So hope you understand the implementation of ANN using Keras for a regression problem. So almost similar thing will be happening in case of the binary classification problem also. Same stuff. Only thing is you have to change the loss function. For the binary classification function, we will use the binary cross entropy instead of the MSE, mean square error. For the regression problem, we will use the mean square error. For the binary classification, we will use the binary cross entropy. For a categorical, that means multiple classification problem, we will use the categorical cross entropy loss function. That's it. Maybe you have a doubt, what is the binary cross entropy and why we will use it? Actually, binary cross entropy loss function means that is used for the binary classification problem. It is a y minus y, actual value, log of predicted value. Minus 1 minus y is the actual value, log of 1 minus yp, predicted value. So this is called as the binary class entropy loss function. This loss function is used for the binary classification problem, where the regression problem we are using the mean square error. Why we use this binary cross entropy loss function for the classification problem? Small Excel I have prepared here. See, actually, let's assume your predictions. Actually, binary cross entropy means yes or no. Yes or no means your numerical data will be yes or no. Your numerical data will be either 0 or 1. So your values are between the 0 and 1 only. Predicted values will be between the 0 and 1 only. Okay. So that's why predicted values I'm assuming that between the 0 and 1. So 0.1 to 0.9 something. And I'm calculating the minus log yp, and later I'm adding the minus log 1 minus yp. That means what I mentioned here, minus log yp minus log 1 minus yp. So then the plots are like this. For this one, I'm getting this plot, and for this one, I am getting this plot. So now I am adding both. I am adding both. If I add the both, how your loss function looks like? See, when you add these two, then your loss function looks like a convex function. So then you can go with your gradient descent method, which will work well, because your gradient descent method will work for the convex function. To get the convex function, we are using the binary cross entropy loss function for the binary classification problem. Only that's the change you have to incorporate in case of the binary classification problem using the Keras. So so this is all from my end. Actually, there are many things are there. Already I shared that notebook with you. So if you have a free time and just work on it. So if you
Sir,
have
where is
any
the
doubt,
notebook, sir? Where is the in the GitHub? You say?
1 minute, sir, 1 minute, please.